All right. I want to introduce myself. My name is Brent Johnston. I'm the Region 6 Director, and I want to welcome you to another quarterly meeting of Region 6. We're going to have a guest speaker today, Javier Provencio, whom I'll introduce in just a moment. Let's cover a couple of things just real quick before we start. Please ask your questions in the chat box. Just want to remind you too that at a time that the 2023 conference, the national conference, is not all that far away. It's in May 16th through the 18th of next year, and it's in San Antonio. So those of you, especially those in Texas, it's a very short drive from where you are in most cases to get to the conference. So I say that because abstracts for papers or presentations is due on the 1st of November. Want to keep that in mind. Membership dues, you still have a little time to renew at the old rate. You've got until October the 1st, so because dues are going up this year. So if you want to lock in at the old rate, go ahead and do that. And also too, I want to remind you that we're always looking for guest speakers from aerospace companies or any company if you're a member of ICEAA for upcoming events. So please email me. For today, post your questions in chat, and we'll select them for the speaker. So let me introduce our speaker here, and that is Javier Provencio. Javier is an affordability engineer at Lockheed Martin RMS. He graduated from Southern Methodist University with a master's degree in systems engineering in 2014. And he graduated from the University of Texas at El Paso with a bachelor's degree in mechanical engineering in 2011. He's written 2 books. The first one is a book called Cost Analysis, Marching to My Own Drum. And the second is Leaving a Fingerprint, a blueprint towards cost control of aerospace projects. He's an active member of ICEAA. He's currently a Region 6 representative. So this is your opportunity to ask questions about the presentation, his books, or just to exchange ideas on the topic of affordability engineering, which is what we've asked Javier to talk about today. So Javier, it's up to you.
Thank you, Brent. When Brent asked me to make a presentation about the published books, I went back and looked at the reason I wrote these books, and it took me back and it re-energized me of how to connect with engineers, how to connect with supply chain management, prod ops, and finance folks, how to speak their language, but in math terms, right? So when I started in the industry, I worked commercial helicopters, and there was a gentleman about to retire, and they said, here's a bunch of Excel files, look through them, and I need you to do cost control on these programs. And it was a lot of learning. So I took all those lessons learned, all those best practices of how to influence programs for cost design. And then after a few years, I said, you know what, let's put this on paper. I think it's value added to somebody that's coming into the industry doing cost analysis. A few years went by, and then I said, okay, now let's look at how do you evolve a culture? How do you change a mindset? How do you influence personnel, which every company says is their best asset, right? So how do you do the human portion of it, right? So took some time and wrote techniques of how to influence folks on all those, right? I've worked commercial helicopters, military helicopters, private jets, jetliners, fighter jets, missiles, and now military helicopters again. So I've been in different programs, and all of them with an emphasis on influencing IPTs, influencing how do we go about the make-buy strategy, how do we go about trade studies, how do we empower engineers or empower the team to make a configuration that does not have cost challenges, or you have cost out in the back end, which we know it requires a lot of NRE, requires a lot of testing as well sometimes, right? So tooling redesign as well. So took all those and created them into equations, looked at techniques and strategies, and I'll share this. There was this one time on a program, we were just getting started, and a gentleman just got off the phone with somebody and said, "Hey, I just got off the phone with my buddy. He said the next program that we're working on needs to be lighter and cheaper." And it was like, wow, thank you. But what that felt short of is saying, here's some techniques, here's some strategies, here's some equations that speak in the language that engineers do. So presentation today takes a couple high points of the books. There's a lot of different things we spoke about in the book. But I'm taking some equations, and then each slide will build on the next slide, and it will make sense. So if you have questions, please put them in the chat, and then we will get to them and swap ideas, exchange ideas, answer any questions for you. So let's get started. So here's an overview of the first book. It's broken down into 5 sections, and all of these were just high-level lessons learned, working different programs of, hey, this is important for cost control. This is important. As an affordability engineer, design to cost, value engineer, whatever title is used in your organization, we touch all swim lanes, and all swim lanes impact us. So as you're going through pre-design, detailed design, low rate production, full rate production, or you're doing maintainability and reliability improvements, these items that you see on the screen do impact your cost, and you need to provide the team some mathematical feedback, equations, techniques of how they can make those decisions, right? Cost does not win all battles, but you want it to be a consideration into the decision. Normally, it's weight. You can do that quickly. Performance impacts to the platform, reliability, safety of flight. Usually, cost sometimes is an output of those. We want to make it into input into that decision making. So we'll highlight some of these. We'll touch on some of these items. The first one, and I was thinking about this yesterday, Y equals MX plus B. Whether you got a bachelor's in supply chain, business management, engineering, whatever degree you got, you had to take this as a basic course. I will convert this equation into something that is usable by the engineer. We'll talk about that in a little bit. As well as when you are on a program and it's fluid and you're evolving, you're getting new requirements by the customer, things are changing, you're getting new loads, drops, you're evolving from pre-design to detailed design to low rate. There's a lot of changes that are occurring. You need to keep up with them, a lot of memory retention to provide feedback to the design team of where their cost is going, providing a cause and effect of where the decisions are leading the projected cost to. The next one is understanding the sustainment portion of it, understanding by changing from aluminum to titanium, what does that do to your recurring costs, simultaneously knowing what it does to your dollars per flight hour, right? This is very common on some platforms and really not on others, just because some platforms just have a one mission, one life, and then it's over. Some platforms live for 20, 30, 40 years, right? So you will see some need for that more in fighter jets, more in commercial helicopters, military helicopters, versus a satellite, a missile. Here's an important one, and we'll touch on this one, is the process versus charge labor. Now, I've seen it from different organizations. I've been part of different organizations. The accounting changes by organization A versus organization B. When you're doing cost analysis, you need to understand how that company does their accounting so you can provide feedback to the design team and make sure you don't double dip or understate the cost of a given configuration. We'll get into that. Understanding the key performance parameters is very important. Always keeping that in mind as you're evolving during your configuration. I've had several situations in the past where somebody says, hey, there's an alternative configuration. We like it. It improves our performance, but the platform is already over cost. It's like, I appreciate it, but we still need to solve our cost issue before we start improving performance. All right, so busy slide. Let's get into the top left. Y equals MXB plus B can be broken down into B is a constant in an engineer's mind, right? If you pick aluminum, whether you're buying the part from Canada, US, Mexico, whatever country it is going to be, it's almost a constant. Yes, there's a little bit, but it's considered a volatile commodity. So you can consider it a constant independent of what country you're buying it. MX would be your manufacturing rate based off that commodity, that part. And then the other variable is going to be your manufacturing hours, the total hours it takes to create that component. So let's take an example. You have a machine part, right? So your B, which is your constant, if you look on the far right, is going to be your length, width, thickness, density, dollars per pound, and scrap factor assigned to that raw material. So then you've solved for B, and then you got to understand what the wrap rate of that supplier is for that given region of the world, for that state, province, wherever it is. You got to understand the wrap rate, and then the time to make the part will be based off your drawing notes, your requirements on the drawing. So let's say going with our machine part, it says, hey, after you machine it, I need you to do a penetrant inspect. I need you to iodine prime. Some parts need shot peen, some parts don't. Whatever is on the engineering drawing, you need to be able to model the projected hours for that part based off your financial boundaries, which would be your platform profile, how many units you're projected to make, and how many are you going to do per year, right? So those two variables will help you set your boundaries of how many hours it's going to take to make a part. You multiply the wrap rate times your hours plus your raw material. In ballpark, you have a part cost. These are the techniques that over time I was like, man, this is a simple equation. Y equals mx plus b. Shared it with engineers. Shared that, hey, you could look up the density for titanium crest, whatever material that you guys are looking. And this is talking machine, right? You could get into composites, you could get into wire harnesses, all different commodities that are typical in the aerospace industry, and apply this equation. And this is going to get you in the ballpark. Is it going to be exact? No. Is it going to get you in the 80 percentile, 85 percentile answer? Yes, right? Unless there's this glaring item that you missed, or that when the drawing is released, they added this post-process operation or requirement on the drawing. Your Y is going to be in the ballpark. A good equation. This translates very well to all engineers, and this helps them when they're doing trade studies, whether it's early in the morning, late at night, during the weekends. They can compare different configurations. One example I'll give you, and it's not machined, it is going to be composite, right? So a designer can say, hey, I can do this composite part. It's going to be 7 glass plies, which is very cheap, dollars per pound for material, more plies, which is more labor, or I could do carbon fiber, which might be 4 plies, but the dollars per pound is a lot higher, right? You take those two variables, you do your analysis, and then they could compare Y versus Y prime. Those are the types of techniques, strategies that the designer can take back and do their trade studies as they're comparing. Should I make this keel a machine keel, or should I do bent sheet metal with stiffener, hardware, subassembly? Which one is cheaper? And doing this simple equation allows them to have a data-driven notional direction of letting the numbers drive the configuration. It's not dollars per pound. It's not, we're not making we're not buying tomatoes from Walmart. It's actually taking what's on the drawing and doing a bottoms up estimate. But this one more thing on this slide is it captures your scenario, which is your production rate, your supplier labor rate, your batch run. It accounts all the manufacturing processes, the dollars per pound that you're buying for your raw material. So it's very specific to your user case. So building on this slide, moving on to this one, what I want to show here, right? So let's start on the bottom left. Let's say you start on a configuration and follow these two lines, right? So you have one line that's angled steeper than the other one. But the main takeaway here is when you start a design, it starts simple, which is A. And then as you get updated loads drops, maybe that configuration is no longer the cheapest option because now you have negative margin on a part and you got to beef it up, whether it's composite, machined, sheet metal, etc. You have to have that memory retention to understand you gave the team direction to stay with that simplified concept. However, due to changes, you have to potentially revisit that Y equals MX plus B, and maybe B prime becomes the cheapest configuration. Sometimes we don't do this, and sometimes we end up with A prime when the cheaper option was B prime, and that ends up happening. That ends up being a cost reduction initiative that ends up costing NRE, testing of the component. So it's a lot of dollars to redesign to end up at B prime when the affordability engineer could have been looking at the configuration and say, we need a pause. We're no longer cheaper by staying on a configuration. Maybe B prime is the cheaper option now. But initially you were correct because A was a cheaper option than B. Things changed over time. Now B's prime is a cheaper option. So always be aware of that. Always be providing the designers, supply chain, etc. Feedback on, hey, let's pause. Maybe we should revisit this. And the takeaway, the math will guide you on what selection it is, and it's making sure that financially you provide the best input. They might still go with A prime for other reasons, but as a design to cost value engineer, you're still providing cost input into their decision. And there it is. Y equals MX plus B, and you use that over and over, and it's broken down from a bottoms up strategy, right? Now, I will pause here, and sometimes you have situations where the designers say, well, I don't know yet, I don't know the requirements. If you become familiar enough with the commodity they're working with, you could guesstimate what the post processes are and start building a shell of projected costs for that design. But it is important to make those decisions early while you could still influence the configuration before it becomes solidified. And now you're talking NRE to change the part. Now you're talking testing dollars. Now you're talking schedule slip, right? Your biggest impact is when the configuration is still fluid, making assumptions, educated assumptions, and driving the team towards cost control at each IPT level. Going to the next item, connecting your recurring costs with your dollars per flight hour. It's very important that you understand and you have live metrics of, hey, if I change this from crest to aluminum or from aluminum to titanium, what does that do to my dollars per flight hour? There's an easy equation, simple equation, another technique in the designer's toolbox that can be added, and they can do those simulations. I never try to predict what's going to happen, which configuration is cheaper. I always just stick to the process, respect the process, apply the cost of the variables, and then it allows us to understand the dollars per flight hour or the recurring cost impact. And then based off those two, you can make a decision of here is the best configuration to move forward with. Conklin and Decker is a very good source. They have a document that outlines how aerospace standards are for accounting for cost. And you'll start with daily inspections, life limited parts, unscheduled inspections, power plant cost, fuel consumption, and what boundaries are used for that fuel consumption, right? Third slide right here is the understanding of the accounting principles of that company, right? So what you don't want to do is understate the dollars per hour for that site or double count a manufacturing process that was part of their overhead. Everybody's different. You have to look at the shop floor travelers to understand how folks do their accounting. Sometimes, again, sometimes it's discrete, sometimes it's charged to the part, sometimes it's part of the wrap rate. Understanding those so you can apply the proper wrap rate to your Y equals MX plus B equation. Now, as time evolves, right? Aerospace projects take significant time for numerous reasons. It is important to keep the vision of cost control in everybody's mind, make sure that they're always thinking of cost as they do these trade studies, as people retire, move on, take on new roles, et cetera, et cetera. It's always good to have it in front of people, the key performance parameters, making sure that they understand that there's resources available to help them do those trade studies, that there are tools that we can share and help them as they navigate which design direction to go with, and helping others be self-sufficient, autonomous in doing those ROM analysis, back of the napkin analysis, and that helps them in their trade studies, that helps them in their design release, that helps them ensure that they are making the best financial decision for the company, stakeholders, and warfighters. So we'll move on to this area, which is the second book. When you're getting into organizations and you are sharing different techniques, it might not be the Excel file that was used. It might not be the dollars per pound that was previously used in a program that was launched in 1983, right? These techniques are switching from a top-down to a bottom-up perspective. And sometimes it challenges the way we've done things. It pushes the comfort zone of folks. So it's always important to understand that. It's always important to know the human element of that and be able to navigate, even though you have the mathematical equations, you've broken it down to length, width, and height times density for that composite material, titanium, whatever it may be, and you have all the data, it still pushes on that comfort zone, and you have to understand that. And there's ways to be a change agent. There's ways to evolve a culture and get people on board of, hey, um, we might have overpaid for that component, or those hours might have been overstated. And the second book starts going into that. The second book starts sharing different scenarios, uh, different personalities that you will meet along the way, and how do you bring them along? How do you encourage folks to maybe look at it from a different angle, maybe look at it from a different lens? How do you do that, right? So again, this is experiences over the years, and then just put them on paper over time. And these books, each of them took a year or so, and just putting things on paper, and then eventually putting them on a document, and then start cleaning it up. But these are based off different cultures in different companies, different business areas, and my observations of the personnel. But I eventually went back and provided more techniques, more phrases that you can use to shape a conversation, to bridge that gap of top-down parametric, historical, to lean forward, be a change agent. Again, these were mentioned earlier. Every company's unique, and these are all observations of those growing pains. This is an example again. Brent said you have some time, so I had to look through some of the pages, and there just wasn't enough time to put everything down and get into the weeds of everything. But there's a lot of techniques in the first book. There's a lot of examples to shape conversations in the second book. I just wanted to put some on the screen that kind of shared of a high point, a graphical image of what the topic is, and then a takeaway at the bottom. You might not be able to see it, but on the top left, it is understanding the cost. And if you remove a cost, how much should the supplier remove from their updated unit price? That second item is, if you add a requirement, understanding how much that in touch time hours that is, so you understand how much your part cost is going to increase. I'll tell you one thing. I've had a situation where I have a machined part, it was seeing negative margin, so they had to beef it up. Well, the supplier said, before it weighed 1 pound, now it's 1.5, so I'm going to have to increase the cost. And I paused and I said, help me understand that. My billet size is still the same. In fact, you're even machining less out of it. So how is the price going up? Help me wrap my head around that, right? So it's having those data-driven discussions with the suppliers, with the estimators, whoever it may be, to understand the cause and effect of design changes. And I went on, and there's some examples of cut-ins and what happens to projects. You'll see in the back different learning curves and different colors of money for IRAD, and you'll see in the middle one. So a lot of different techniques to shape the conversation, to phrase the topic and tailor it towards an affordability, value engineering, design to cost perspective. My goodness, that was a lot faster than I expected. Any questions in the chat?
Yeah, Javier, let me ask you a few questions here. So thank you very much for the presentation, for taking us through this. I think you've got a lot of knowledge, a lot of experience doing this effort. So I think your insights are pretty valuable. So what kind of tools or models do you find to be useful for cost analysis?
Over the years, I've looked at numerous tools available in the industry. There's new ones coming on yearly, and all of them have their strengths, all of them have their weaknesses. Half of it is the tool itself, and then the other half is the affordability, design to cost engineer, right? So it's understanding where the program is, where the schedule is, how much NRE is left, what's the make buy strategy, how much footprint we're looking at. All of those factors are not covered in the software. So it's a blend of understanding systems engineering, understanding how programs work, and the other half is the software itself. And the software is a big old calculator, right? There's a lot of proprietary information that makes that software very powerful, but it's not powerful if the affordability engineer has all this raw data, numerous engineers looking at them and saying, help me decide configuration A, configuration B, right? So plenty of software out there, Brent, to look at to help your organization, whether it's aerospace, automotive, oil and gas, whatever it may be.
So Karen Maricas has a question for you. So Karen says, can you speak more on performing trade studies incorporating cost, in particular for complex trade studies at the larger platform level rather than detailed lower level parts?
Absolutely. My approach has always been, if you can switch from a top-down perspective to a bottoms-up, it will be beneficial for everyone. And what I will say is, you can work with your configuration management, with your mass properties, weights engineer, get a bill of material, and then start making assumptions with collaboration with the engineer of, what material do you think this is? What kind of post-process operations are you going to do? Are you going to require tap testing? Are you going to require scanning? What kind of heat treatments do you need? All those basic questions you can get from the designer, and then start forming a cost of each LRU. Is it easy? Absolutely not. Is it complex? Yes. Is it possible? Absolutely. And then you could start providing cost to the groups for configuration A and configuration B. And secondarily, right, as you're building up these two configurations, you start asking questions that are organic, that people shy away from, such as, what is our make buy strategy? Okay. What internal sites are we going to build these parts? How are we going to integrate this? What kind of capital are we looking at? You start asking the organic questions that are there. People have an idea. They just aren't ready to pull the trigger, and you start just drawing them in and saying, yeah, hey, what are our core competencies? Or what are we going to farm out, right? So the change from top down to bottoms up is beneficial, because you start getting into that fidelity of the configuration, of the routing of components, attachments, subassembly, all those organic questions that usually happen at the very end. And it's like, oh, we forgot about that. if you're able to capture those, ask those questions early on, and simply just by having a bill of material and just asking the basic questions. Hey, what is the plan? I'm not asking you to, sign and this is the official path forward. I'm just, what are you thinking? Let's kick the can around. Let me get something and then let's put it on paper and then move on. And then if things change, we will adjust. It's no big deal. It's just giving us notional direction of what configuration A versus configuration B. Now, I will take a step back, Brent, and say if you're so far along upstream and you just have um, models and there's not that much definition around it, it gets a little bit more complicated because you don't have that structure behind those shells. So at that point, you're still in a dollars per pound parametric world. Ideally, you want to switch from that to a bottoms up as quickly as possible, because then you could work your magic. Then you can start driving the teams and giving a cause and effect of what their decisions are on the unit cost.
I mean, that's the challenge, right? I mean, it's, like I tell people around here, it's what do you know and when do you know it, right? So if all you know is not much more than, well, this is what it weighs and this is the rough material composition, then that obviously limits the approaches you can go use. But to your point, if you can force some level of definition, but you're not talking about, I mean, you don't have to have every bracket, every systems bracket defined. You don't have to have every fastener defined. I mean, in the approach that you're talking about, you can at least, as long as you've got the big bones of structure, that's still valuable at that point in your mind to go try to convert to a bottoms up analysis.
Correct. And think of it this way. You're sanding the corners, right? I think I call it sanding the corners. I've called it for years. You're taking that bill of material and you're just refining it over and over and figuring out where people are going to add clips eventually. They haven't modeled them in the drawing tree yet, but they're going to lean towards that. And you're like, hey, how are you going to attach this? And you start asking that, and then you start populating your bill of material with dummy part numbers so you can account for the cost, and then you can start maturing the model. Even though the design team is not there yet, you're starting to add fidelity and you're starting to raise a flag when they're over their allocated budget, or there's some opportunity to collapse some of those parts into a larger machined item or composite item, 3D printed, whatever it may be. Then you start looking at the data and providing feedback. Hey, maybe we can call out the same part number twice, which collapses some of our bill material. It adds quantities to the supplier and they're happy, et cetera, et cetera. So yes, it's rough. You can start making assumptions and just adding fidelity, even if the design is on paper, the drawing tree is still not there yet.
So what do you find are the most common misperceptions that engineers have about cost and cost analysis? What are they, when you sit down and talk to them, they say, oh, gee, I never knew that, or I never understood that?
All swim lanes that I've worked with are very talented, very smart. They understand math. The techniques and strategies have not been shared with them of how to navigate this complex world of affordability. By providing them techniques and strategies in their arsenal, they're able to be self-sufficient. And I'm not saying provide all that information and then it's hands off. It's giving them the information, following up, looking over their shoulder, and making sure that they're understanding the information, right? Dollars per hour for the manufacturing site, understanding what a requirement does in terms of touch time, in terms of span, in terms of rework, scrap, et cetera, et cetera. That to me is the biggest challenge that the organization has. Is everybody says affordability is good, and nobody's going to disagree with you on that. It's providing those techniques, providing that mathematical calculation that allows them to really look and figure out which configuration is better. Um, when you convert things into dollars, it's very interesting where it's a new world for folks, and they don't want to get their feet in the water. They want to just they're a little bit shy, but I have mentored folks over the years and provided them techniques and strategies, and part of my development as well is seeing how good do they capture the information, how do they retain it, how do they apply it at their next opportunity, how do they go about doing trade studies and using all the resources, Excel, using your internal SAP system to look up part costs and understanding uh, how to apply these principles for their configuration, for their objectives. Oh, you're on mute, Brett.
Sorry. So certainly one of the experiences I've had over the years is that there's not a good understanding in the engineering community about how the accounting system works, and certainly how overheads and fringe and G&A and all that stuff gets applied. I mean, that's always a big mystery, and that kind of gets back to your Y equals mx plus b. It's understanding that m function about, what is how many dollars per hour it is, what's the wrap rate. I find that engineers just don't understand that, and why would they, right? It's not really in their swim lane. Have you found that as far as misunderstanding about how accounting works and all that?
Correct. Yes, and it's a very important. Smaller companies do the accounting a lot different than larger companies. Going back to a slide that I shared earlier, where you had a supplier that has very little overhead versus a supplier that has some overhead. Theoretically, those two should balance out. I've thought about this over the years, and it's very similar to a high deductible insurance versus a low deductible insurance. It's almost a wash, right? So, but the key there that you mentioned is understanding what is charge labor, understanding what is process labor. One of the easiest ways that I've found is working with the manufacturing engineers and industrial engineers and looking at the work travelers, work orders, whatever your organization calls it, looking at those. And as they say, operation 10, 20, 40, et cetera, if there's a standard time, then it's direct charge labor to that component. It's not part of their overhead. So as you do your modeling, then you can account for those as discrete manufacturing hours, and then you multiply it times a wrap rate.
So as long as I've been in this business, which I just crossed 35 years earlier this month, gonna age myself there. It's been a goal that one day, people always say this, one day we'll have a tool that it's going to provide the design engineer a real-time estimate. So as he's working on a CATIA monitor and he changes a part from sheet to machined, if he changes this from aluminum to composites, it's going to spit out the answer and tell him, hey, here's what the impact is, here's what the cost impact is. How close are we, in your opinion, to actually getting to that utopian state? Are we years off, or do you see it as a possibility with the whole digital transformation and artificial intelligence? Is that a feasible goal for the future?
It is. And here at LM, we're working on some secret sauce that is getting us there. Not much more can be said about that, but we are on a path to get there.
Because I mean, that's always been the goal, right?
Yes.
That ability to go to go from CAD to cost. Karen Maricas has a great question about that. So of course, that's always, of course, a system like that's always got to have some guardrails. I don't think it's possible for it to be completely autonomous because, again, the engineer doesn't necessarily have a full understanding of the accounting and so forth. And so I think you're
Yes.
always going to have somebody in the loop, right? Is that the way you see it, or?
Yes, and you're still going to have some oversight. You're still going to have the need for an affordability engineer to be part of the process. Think of it as an independent auditor of the configuration. Think of it as a person looking from the outside, not having any interest in what the configuration is. You're just looking at the dollars. You're still going to validate that a designer did not fall in love with a given configuration and maybe tilt the scales a little bit. You're always making sure that the company's best interest is at every core decision along the way during pre-design, detailed design, low rate, full rate, and sustainment environment. So there will be a need to have an affordability engineer helping, and just like every software, there's limitations, but we have a path to mitigate those risks.
So how often do you find that to be the case where engineers fall in love with their own designs and don't want to see anything wrong with it?
We've had a few. We've had a few over the years. And it's having that data-driven discussion of why this configuration versus that, and showing the data, and then it becomes about discussion of why you chose MX, why you chose B. And those are the detailed discussions. And, you know, there's going to the second book, there is an idea in an engineer's mind that if I've been working on this design for 3 months and I have to change it, I don't want my PMP, I don't want my Atlas, I don't want my yearly evaluation reflect that they had to scrap my design and then switch paths in the middle of it. So there is that feeling that also influences trying to force a round peg into a square hole. It's a very interesting dynamic, but it's always just approaching it from data, looking at the numbers, and that's all, and letting the numbers drive the decision, drive the configuration.
So let me ask you about another dilemma that I'm sure you've come across in your career, and that is that, at least on aircraft programs, and this is probably true in the helicopter world too, there's always a weight problem somewhere in the design process. There's a recognition that the aircraft weighs more than it should. It injures the performance, and there's all of a sudden a huge drive to cut weight out of the aircraft. And as you know, there are decisions that will save weight, but it'll increase the cost. So what is your experience in those kinds of situations? How do you stop the company from doing something that's not very bright when there's all this pressure? We got to get the weight out. We got to get the weight out. We're going to lose the program if we don't get the weight out.
Absolutely. So a good example I can provide is early on in my career, you know, I sat next to the weights guy, and we teamed up, right? Historically, he wants to make everything titanium and I want to make everything steel because it just helps our metrics, whether it's cost, whether it's weight. We decided early on to team up. There was going to be some parts that were going to be titanium and some parts that were going to be steel, but we looked at the data and we compared it, and we made those decisions. We were partnering to make sure that the payload and the cost were working hand in hand, and we were not working against each other. And trying to make a matrix of the best cost and the best performance.
So have you seen people in the past, have you been involved in programs in the past that tried to quantify that relationship? Like I've seen some programs say, you know, here's the value of a pound, that if I can save weight and I can keep the cost from going up no more than, pick an amount. Okay.
Yes.
So you've come into those.
Yes.
So what's your opinion on those? Does that work well?
That's a rule of thumb that works well, and it helps you navigate during pre-design where things are just so vague. And going back to the question earlier, where you just got CAD shells and you don't have that definition behind it. You don't have the structural load paths and the EQ folks getting involved, and you don't have all those details yet. You need you need a beacon. You need a notional direction of where you need to draw the line, whether it's going to be titanium or it's going to be aluminum or steel. But yes, to answer your question, correct.
So to talk a little bit more about weight, so I think it's safe to say that you're not a huge fan of weight-based parametrics, that you would prefer to work at a more of a bottoms-up approach, preferably at maybe a standards-based approach if possible. What do you think are the major weaknesses of a weight-based approach?
Great question. So top down, the risk is that you're leaving fat on the table. Bottoms up, the risk is that you're not accounting for enough of it. So there's risk both ways. I still believe to move forward, to stay competitive against the company across the street, across town, across the country, you have to transition to a bottoms up approach as soon as possible. And this includes helping folks develop standards for the final assembly line, helping folks understand how you're going to make Mr. Potato Head come together in the final assembly line, and what you're going to farm out to suppliers, how you want those items to come in, how your install drawings are going to come together, helping folks navigate all those decisions early on, and having that dialogue is beneficial versus a top-down approach where makes so many assumptions. And yes, it's aerospace. Yes, we do have standards that everyone has to meet, but each cost analysis is a unique snowflake, and you have to, as a design and cost affordability engineer, you have to look at those. You have to help out.
So when you're performing bottoms up, talk to me a little bit about what you perceive as the advantages of, hey, I've got a model and it's mostly homegrown in terms of it's going to be based on our company's standard space, how we look at things, versus taking a commercial off-the-shelf model. So what do you think are the advantages and disadvantages of each of those?
That's a great question. Internal models are very good at predicting what your internal sites have demonstrated. Commercial models allow you to compare yourself to the industry. You don't know their secret sauce, but you know somebody's been able to align the stars and make a component for X amount of hours. You don't know what CNC machine, you don't know what oven, what tooling approach they took, what trim, drill, etc. You don't know those details, but you challenge the engineering team and say, hey, I don't know how they got there. Here's a unit cost. I could do some modeling for y'all. and see what you could do. And that induces that creative freedom of the engineer to say, let's see how I can shave off 10 more hours of this design. Let's see how I can look at this and maybe question if this is a need or if this is a want requirement. That's the difference is homegrown models will help you project how you've performed internally and help you not be at risk on a contract relative to your demonstrated performance. Industry allows you to compare yourself and really say, am I still cost competitive? Is my IRAD making sure that I buy enough capital to stay competitive with the guy across the street? They both have advantages and they both have disadvantages. It's understanding how do you continue staying competitive with these new startups that are usually, hungry.
All right, I think we're getting close to the hour here. So this is the last call for any questions that the audience has. If there's anyone who has a question, you've got a few minutes here. I'm going to run through a few points. I hope that you were able to take advantage of some of the recent things we've had out there at the OEM COG. I gave a presentation on second source manufacturing. Yesterday was the 2022 ICEAA all member virtual meeting. There are several events that are coming up that you might be interested in. There's the Project Controls Expo in Washington is on the 4th through the 6th of October at Nationals Park. On the 28th of September, the Southern California chapter is going to have a presentation on digital engineering. And it will be a lady from the RAND Corporation who is putting together a study for the Air Force on digital engineering. I've seen the presentation. It's very interesting, especially if you're new to the concept of digital engineering. You don't know really what that means. What does that really entail? I highly suggest that you reach out for that presentation. You don't have to be a member of this Southern California chapter to join in that. And then on the 4th of October, the Washington chapter has a presentation on using technology readiness levels to go predict the future of nuclear weapons, which, well, that sounds like a good topic, right? The next meeting that we will have will probably be in November. We don't have a firm date, and we will ask John Deem to talk a little bit about design to cost. So that should be very informative. Recording of today's presentation will be available on the ICEAA website in a few hours. And typically these are also on YouTube on the ICEAA channel there. So you can catch it on either venue. Any questions? Anyone? No? All right. Well, then I'll close up. Javier, thank you very much. I think that was a very interesting presentation, and I think some very good comments, very educational. And that's it. So thank you very much for joining us today, and please join us for our next meeting in November. Thank you.